Okay, so the second speaker for the second session is Evan Sorensen from the University of Wisconsin-Madison. Take it away, Evan.
Thank you. Glad to be here. So this is based on joint work with my advisor, Timo Seppäläinen. I want to introduce the model of Brownian last passage percolation. So maybe you've heard of a last passage percolation or first passage percolation before. Also directed polymers. These are all models in the KPZ universality class. So Brownian last passage percolation is in some sense a cousin of these models. It's a nice model because it has one continuous parameter, one discrete coordinate. And so it's somehow an intermediary between the discrete last passage percolation models and things that are fully continuous, such as the KPZ equation, directed landscape. And so it's used in a lot of analysis, understanding how we transition to these universal models. So we start with these IED Brownian motions, one for each integer. And here we've graphed this. In the plane, we have integer levels. And we're looking at paths that take upright steps. So they move up and to the right. They're moving from MS to NT. And we're trying to find the maximum of all sums of increments of the Brownian motion. So along the first level M, I have an increment from S to SM. Then I move up, I have an increment of the next Brownian motion on the next level. And I'm taking sums of all these increments of Brownian motion and trying to find the maximum. That is the last passage time. And the path that achieves this is called a geodesic. One object we like to study with these models is semi-infinite geodesics. So we have some initial point, we say MS here, and it's going off to infinity. And it has the property that you take any 2 points, for example, KU and RV along the path. The portion of the path between those 2 points is a geodesic itself. That's for any 2 points. So existence of finite geodesics is just a trivial exercise with compactness and continuity of the Brownian motions. Existence of the semi-infinite geodesics is much more difficult to prove, certainly not trivial, and so it takes some work to show that these exist. So in a lot of models, and it turns out to be true of this model as well, we expect that all infinite geodesics will have some direction. So by that, we just mean that if you take a sequence NTN along this path, then it's going to have a limiting slope, and that we call that theta for this model. So there's a few ways that in these different kinds of models that we study infinite geodesics. We take the approach of Busemann functions. So these first were used to study semi-infinite geodesics in 2008 by Christopher Hoffman in first passage percolation. In this model, we're defining Busemann functions as we have 2 initial points here, M0 and MT, and they're both traveling to the same terminal point, N theta. And we're looking at the difference of their last passage times as n goes to infinity. Let me just give a heuristic why these should exist. The geodesics will tend to coalesce much earlier than the terminal point, at least for n large. So we'll call this coalescence point Z. Now, as n changes, this coalescence point could change, but it makes sense that it should stay around the same. And so the difference of last passage times is just the difference of last passage times up to this point Z. And so it makes sense, at least heuristically, why these limits should exist. Of course, there needs to be some rigorous justification for this, and so using a coupling technique, this was proven in 2019 by Albers, Zuaga, and Simper. They show that if you fix theta and fix t with probability 1, this limit exists. But there's uncountable many values of t and uncountable many values of theta, and so showing this, so there's a global process where we can define these Busemann functions. It takes a little bit of work, and that was one of the first things that we did in our paper, is to extend this process to a process for all t and all theta simultaneously. As a process of t, this is a continuous process. But as you vary the parameter theta, we have some discontinuities. And so we have these theta minus and theta plus processes that are the left and right continuous versions of the process as we vary the parameter theta. One thing we can prove is if you fix the value of theta, the theta minus theta plus distinction is not there. So I mean that as with probability 1, h and theta minus will equal h and theta plus for all values of t. So the values where there's a different are random. Turns out to be a countable set. And for that, so if we fix theta, it's understood that it's fixed, then we're going to drop the plus minus distinction, just write hm theta. And this is as a function of t, it's a Brownian motion with drift. The drift depends on the direction, and as the direction increases, the drift gets smaller. So I want to show maybe some heuristic for how we use the Busemann function to construct semi-infinite geodesics. There's a construction for discrete models. This one's a little bit more nuanced because in discrete models, you just decide, okay, at each step, do I move to the right or do I move upwards? Here we have to decide how far to the right do I have to move because there's a continuum of parameters. So it requires a little different point of view. So we start thinking about this. Just think about, finding a geodesic between ms and nn theta for a large n. We want this geodesic to go in direction theta. So let's just think about having a geodesic that goes to this point and say n is really large, and somehow we're going to take n to infinity and get an infinite path. If I want to figure out what my geodesic looks like, I can actually just figure out what my first jump time is. So I'm going to maximize this quantity here as a function of u. So I'm going from ms to nn theta. BMU minus BMS is my increment along the first level. And then I jump to level m+1, and I have a remaining passage time from m+1u to nn theta. So we call this the dynamic programming principle. We can find the first jump time by maximizing this quantity. Okay, so equivalently, we can maximize this other quantity. So what I did here is I removed the BMS. That's just a constant in u. And I subtracted off lm+1, 0, and then that's a constant in u as well. So it's the same function, except for I removed some constants, so the maximizers are the same. So thinking about this, I can think about Busemann functions now because I have a difference of last passage times. So at least for heuristically, I think of it sending n to infinity and choosing tau m, my first jump time of my geodesic, to be the maximizer of this function here, this bm minus hm+1. hm+1 is the Busemann function. And I have a maximum from s to infinity. Once I've decided where to jump to the first level, I can kind of repeat the same process. I start from m+1 tau m and decide where should I jump next. So indeed, there's a way to do this inductively, where I start from s. On each level, I take a maximizer of a successive function, and it gives me a sequence of jump times. So a sequence of jump times, an infinite sequence, will actually define a semi-infinite geodesic. So what I just outlined to you is very heuristic, but this can be very, very precise. And so this theorem says that every sequence constructed this way does define a semi-infinite geodesic, and it has the direction that we would want. So the direction of the Busemann functions corresponds to the direction of the semi-infinite geodesics. I'll stop here quickly if there's any questions about this, this construction. Okay. So because the Busemann functions construct the geodesics, it's, if we understand the distribution of the Busemann functions as the parameter theta changes, it'll help us understand the global collection of all geodesics. So we have some theorems that describe the joint distribution of Busemann functions for varying parameters theta. Remember that every function, as a function, if you fix theta, every function is a Brownian motion with drift. And so we have these theorems in terms of these queuing mappings that describe as you change the parameter theta, what they look like. Here's a simulation of this. Notice I have lots of Brownian motions with drift. The drift is different, but it's very interesting the way that they're coupled together. So the Brownian motions stick together for a while, and then eventually they'll split. And after they split, something very interesting happens. If you look at, for example, the yellow trajectory and the green trajectory, every increment of the yellow trajectory is larger, or could be equal to, at some places, to the increments of the green trajectory. So the distance between the curves always increases. Whenever there's a splitting point, there's an exceptional value of theta, where the theta minus trajectory follows the upper curve, and the theta plus trajectory follows the lower curve. Here I plotted just, I think, 13 of these curves, but actually this is what the picture would look like even if you plot all and count many of the theta values. If you truncate at a finite level t, for example, this line here, up to that time there's only counting many trajectories. Eventually they'll split off because they often go in different directions, but these are coupled together very nicely so that at a certain time there's only counting many. Okay, so the Busemann functions tend to stick together for similar parameters, and so it has some consequences for the geodesics as well. That they, if you perturb your parameters just a little bit, that up to a finite level, that the geodesics tend to be very close together. And in fact, actually, they match as long as you're close enough. So this has some very interesting geometric consequences. I'm just going to kind of outline some of those. So the set theta is a set of directions where the hm theta minus and hm theta plus disagree somewhere. This is a random countable set. So the following are equivalent. If theta is not in the set big theta, that means that all theta-directed semi-infinite geodesics coalesce. So for example, here I have points x and y. They're both going in the same direction theta. They will coalesce at some point z. So remarkably, this is also equivalent to the following condition. If there just exists an initial point somewhere where there's exactly one semi-infinite geodesic in direction theta. If I can find some point x where there's only one theta-directed geodesic, that means that I'm not in the set big theta. So the consequence is, conversely, if theta is in the set big theta, this exceptional set, then from every initial point, there's going to be at least two geodesics in the same direction theta. And that's the case in this next picture here. When theta is in this set big theta, this exceptional set of Busemann functions actually completely classifies this non-uniqueness of behavior. So when I'm in this set, from every point I have two geodesics. There's theta minus and theta plus geodesics. They correspond to the theta minus and theta plus Busemann functions. So you can see from X, there's a blue geodesic and there's a red geodesic. They eventually split. They'll stick together for a while. Eventually, they will split. And then there's two coalescing families. So the theta plus geodesics all coalesce. The theta plus geodesics from both X and Y coalesce, while the theta minus geodesics from X and Y also coalesce. And they stay apart. The two different families stay apart after they split. So this is very similar to some behavior that we see in discrete models. There's a paper recently by it was Chris Janjigian and Firas Uzuaga and Timo Seppäläinen that had kind of a similar behavior for exponential last passage percolation. But what we really start to see some really interesting behavior in the Brownian last passage case is we have this continuum of points. And so we start seeing some interesting fractal behaviors that we don't see in discrete models. So there's a set of points, these points V and W. Those are the points where geodesics split, the theta plus and theta minus geodesics for some direction theta. Now this set is a random set. It's a big measure 0. It has Hausdorff dimension 1/2. So we start seeing some very interesting fractal properties in this model. So that's all I had to say for today. I'll just mention this talk came from it was based on 2 papers. One is on the archive. One should be on the archive very soon. It's just in preparation. It's being polished. I will also give it a talk in the Cumulative Probability Seminar next week on Tuesday, where I'll be able to go into some more of the technical details of this project. Thank you, and I'm happy to answer any questions.